Hello and welcome to Innovative in Education's Organic Chemistry series. My name is Mike Evans and I'm the Organic Chemistry Content Director for IE. Today we're going to be talking about the first elementary reaction step. And the elementary steps, which I alluded to last time, are these fundamental units of organic reaction mechanisms that sort of possess their own sort of properties that are unique to them throughout multiple mechanisms, which is why they're useful for us to learn about and place in the context of larger reaction mechanisms. So the first one we're going to deal with in rather excruciating detail is the proton transfer step, and this is going to take a couple of lectures, but today we'll introduce the basics and take a look at curved arrows and the molecular orbitals involved in the proton transfer step. So just to review a little bit from last time, we looked at frontier molecular orbitals as those that control reactivity. And the frontier orbitals are important because they're those at the very frontiers of energy. So if we look at a molecule as a sum of molecular orbitals that sort of really define all of its chemical bonds and things like that, then the most important electrons in the molecule are those at the highest occupied level. These are the electrons that are the most reactive because they're the highest in energy and the most willing to leave the molecule. We call these the HOMO electrons, and that level is referred to as the HOMO, the highest occupied molecular orbital. The orbital just above that is the most electrophilic, or the most desiring of electrons of all the orbitals. The higher energy empty orbitals don't quite want electrons so much because they're higher in energy, and electrons that jumped into those orbitals would simply want to fall down to the LUMO anyway. And as I just alluded to there, we call this orbital the lowest unoccupied molecular orbital, or LUMO, and it's HOMO-LUMO interactions, or frontier MO interactions, as I refer to here, that really define the electron movements of organic chemistry. And as we already talked about, the movement of electrons is key to reactivity in organic chemistry. Believe it or not, at least for our purposes, we can break up all organic reaction mechanisms into combinations of the elementary steps. There are quite a few elementary steps. We'll deal only with 10 in this course, but using these 10 elementary steps unlocks the possibility of understanding a massive array of organic reactions. So let's jump right into it now with the proton transfer step. So this first slide deals with the basics of proton transfer in terms of what frontier orbitals are involved and what do we call the reacting partners. So you're probably familiar with the names we give to the reacting partners as acids and bases. Acids are electron acceptors. This is the Lewis definition of acids and bases, and I like this definition because it mentions the electron, and I put a huge emphasis on this idea that electron movement is critical to organic reactivity, and you can connect the A in acid to the A in acceptor when thinking about acids as electron acceptors. Bases, on the other hand, are electron donors or proton acceptors in the Bronsted-Lowry definition, and they serve as sources of electrons that pick up protons. The idea of a proton transfer is exactly that, transferring a proton from one substrate to another. And notice that in order to transfer a proton, H+, we have to give up the electrons in the XH bond, whatever X may be, to the atom X. So that atom X is serving as an electron acceptor. It's really serving as the true acid in an acid-base exchange type process. The curved arrows for the process are shown here. So the base here is ethoxide anion, and a lone pair on ethoxide is taking a proton from this molecule on the right, which is acetic acid. Now in this process, we see the new bond forming between this oxygen and hydrogen, and this oxygen atom really serving as the key acid, the key accepting atom that's receiving electrons in this process. It's important to recognize that this is an N to sigma star sigma type interaction. What does this mean? Well, it's an N frontier orbital on the nucleophile that's serving as the donor, in these frontier orbital interactions, we always list the donor first. There are the donor electrons, and they're being donated into the sigma star of the OH bond, and we can see that by noting that the OH bond breaks. Because the bond breaks, we know that a sigma star is probably involved in this reaction. What do these orbitals look like? Well, hopefully you recall from some of our earlier studies that a sigma star has a node between the nuclei and looks like this. An N orbital is simply often a hybrid and looks like this. And the idea that it's sigma type refers to the fact that the orbitals like to align coaxially. So I haven't drawn it exactly right here, but the real orbital alignment looks something like this. There's the N orbital, the sigma orbital line, or the sigma star orbital, lines up perfectly like so to directly accept those electrons through coaxial overlap. So this is how the actual electron transfer happens in donation from the N to the sigma star. It's a sigma type interaction because both reacting partners are free to move, and as we saw before, the sigma type interaction is more stabilizing than the pi type. Kinetically, these reactions are very fast. Because the proton is extremely small, it's very easy to sort of push around, and so molecules will often push around protons very, very quickly. Thus, we reach the situation of thermodynamic equilibrium very quickly. So we saw a couple of lectures ago this idea of kinetics versus thermodynamics, and really for proton transfers, kinetics is out of play completely because thermodynamic equilibrium is established very, very quickly. And this is a point we'll hit on later, but for now, I'll just mention that activation barriers for proton transfers tend to be extremely small. So for instance, in this process, this sort of hypothetical that I've drawn here, we're going to very quickly funnel to the more stable product. And lucky for us, it's often very easy to tell which side of an acid-base equilibrium will be favored. The key is this thermodynamic energy difference between the reactants and the products. So with the introduction of the PT step here, we can now place the PT step on this 9-item grid that was mentioned last time of all the possible filled to empty interactions. This isn't actually the only N to sigma star interaction we'll see. We'll see other elementary steps that fit into this paradigm as well, but this is the first one, and I just wanted to place it there. So keep in mind moving forward that the key interaction for the proton transfer step, which we'll be talking about in the next couple of lectures, refers to an N to sigma star type interaction. Anything you've learned so far about what influences the energy of N and sigma star orbitals applies equally well to the proton transfer step. So keep that in mind as we move forward.